Hi, and welcome to my talk on democratizing stream processing at Zillow. My name is Kelly Smith, and I'm a principal software engineer on Zillow's streaming platform team. And I can't tell you how excited I am to be able to share all of the awesome work we've been doing at Zillow over the last year, and in particular with a group of people who are just as passionate about this space as we are. Before I get into all the details, I want to just give a little bit of information about Zillow and what it is in case you don't know. So Zillow is a real estate technology company, and we specialize in collecting and consolidating property data so that we can give customers a holistic view of the real estate market in their area, including things like our Zestimate, which helps them understand what we think their home is worth, and we use machine learning to generate that. We also help customers get in touch with real estate agents, so when they're ready to take the next step and walk through that transaction experience, they can get connected with a trusted person that can help navigate that process. So as we build all of these services and features, there's a lot of stream processing that gets involved. And so just to give some examples, we obviously collect a lot of property data and process it in real time and bring it into our catalog of properties. We collect a lot of data from the web properties and apps themselves as well, so that we can do things like experimentation and A/B analysis. More recently, we've been pushing machine learning into our real-time pipelines. And so as a property comes through our system, we can analyze it and make recommendations to customers so that they can get notified and be the first to find out about a new property that interests them. And then finally, we also have seen a lot of interest and usage of stream processing in our Kafka systems for bringing data in from a bunch of separate sources and consolidating it into one place. In our case, a data lake, which is where we can then build holistic data models that combine all the various business aspects of Zillow. And so we have data scientists and business analysts that use that data as well. So as engineering teams around Zillow sort of recognize these stream processing opportunities, we saw a lot of interest and a lot of onboarding of these technologies. And I just wanted to walk through an example of what we saw happening around the company and then how we have sort of used these observations to inform what we've done in terms of streamlining the developer experience and building a platform on top of it. So at Zillow, we have this central data catalog, and this is where teams are able to register their data sources, whether they're batch data sets or streaming data sets. We want to bring all of our data into one place. And so as a Zillow engineer, I might find a source of data in this catalog that interests me, and I want to do something with it. And so typically in the streaming case, these would be pointing to a Kafka topic. And so there's a physical location where this data is stored. In addition, we have the Confluent schema registry that we use, and this gives not only a sense of where the data is located physically, but how it is structured, what fields it has on it, and then how I can actually go about deserializing and using that data. So then an engineer might spin up a Flink job to then consume that Kafka topic and start doing interesting things with it, and they would use the schema registry to deserialize that data dynamically. Historically, this was done using EMR clusters on AWS, but more recently we've been moving on to Kubernetes as a central and shared infrastructure, and I'll talk a bit about that in a moment. But then once they've got this Flink job, they have to sort through things like identity and permissions so that their Flink job has the ability to read from that Kafka topic. And then, obviously once they're producing a new set of data, they're going to need to be able to register that new schema within the schema registry. They probably need to then stand up a new Kafka topic so that they can write the output of that job somewhere so they can be persisted long term. Again, they've got to deal with issues of identity and permissions so that their job has the ability to write to that new topic. And then ideally, you would want this new data stream that's been produced to just sort of automatically be represented within that data catalog. And I'll even kind of add to that there's this notion of lineage that we want to be able to capture. So as data quality issues are discovered downstream, we want to be able to trace those back upstream to where they may have come from. And so as our company has grown and as our stream processing cases have grown, this is becoming increasingly important for us to be able to trace accountability of data end-to-end throughout the system. Another common scenario is that once they've produced this new output stream, they maybe want to replicate it to that data lake that I talked about just now. And so we have Kafka connector clusters that allow them to provision things like that. And then obviously into, say, an S3 bucket. And then, of course, you want that same batch data set to be represented within the data catalog, and you want that lineage again to be brought forward from the output stream to the output batch data set. And so just to give you an example of this, mostly so that you can sort of understand that there's a lot of complexity here, and that this was sort of the complexity that each of our different engineering teams at Zillow had to navigate on their own. And so what we saw was a lot of duplication of work, reinventing the wheel, different stream processing technologies, different event streaming technologies. So we had some teams using managed Kafka in AWS. We had some teams using Kinesis. And so what we kind of set out to do is figure out how can we take all of these small and repeatable things that every team at Zillow was doing and build a platform around them and build an experience around them so that they could go from idea to a fully operational production-ready service that can scale without having to worry about all of these complexities and having to deal with all the different sets of infrastructure that end up powering this. So keep that in mind as I go forward, because this is really what informed a lot of how we approached building a platform. And really, I think at this moment, it's important to think about why would you go about making a platform, or why would you need to go make a platform? And really, there's only one reason, and that's to drive down the per unit cost of running your business. So all of the complexity that I just described, it really started to drive up the cost of doing business for us, because we had teams wasting effort building multiple sets of infrastructure. We had teams spending all of their time figuring out how to use these new technologies and how to combine all of them together into sort of a holistic stream processing system. So you had an impact on developer productivity there. And then you had an impact in terms of opportunity costs as well, where if you're spending all of your time standing up new infrastructure and learning about how to compose all of these technologies together, you're not spending your time innovating within your business space. And so the reason that we had for building a platform is we wanted to be able to drive down all of these costs so that developers could focus on innovating within their business rather than all of the daily complexities of running stream processing infrastructure and technology stacks. So as we sort of went from this ideation and this observation of what engineers were doing, we started to form a set of requirements for what our data platform needed to be. The first requirement being that any resource needed to be able to be provisioned in less than a couple of minutes. This is really, I think gone are the days where it's acceptable to submit tickets to infrastructure teams and wait several weeks for things to be created for you. So we wanted our system to be just as good as the cloud providers that our engineers were already using, like AWS. And this means we needed to start thinking about building simplified and consolidated APIs so that engineers could just simply create what they needed without having to navigate all of the complexities of how they were being implemented behind the scenes. And it also meant we needed to look into things like containerization to solve the problems, like provisioning a new Flink cluster, for example, on EMR typically took several days to a week of talking with the engineering teams and figuring out what their requirements were, and then actually getting that physical infrastructure up and running in a production-ready state. The next requirement is that this entire provisioning experience for getting these resources created needed to be completely self-service, end-to-end. And this again goes back to that, it's not acceptable anymore to have tickets for provisioning where you're waiting on another team to do things for you. And it just doesn't scale in terms of having one team having to handle all of this. And so getting to this end-to-end experience required us to solve problems around authentication and role-based access control so that the teams could create whatever they needed in a self-service way, but they couldn't accidentally impact someone else's resources, for example. So there's also a notion there of being able to isolate resources properly so that one set of provisioned stream processing things can't impact another set. It also required us, because we were thinking about having shared infrastructure, that we needed to have some way of applying custom validation logic. So we couldn't simply just unleash our engineers on the Kafka or Flink APIs themselves, because there's just no way for us to prevent someone from, say, creating 1,000 partition topic, sending a whole bunch of data to it, and bringing the whole cluster down for everybody else. The next requirement that we took on is that we wanted to be able to provide a declarative provisioning experience. And what I mean by this is that engineers should be able to tell us what they need and not necessarily have to deal with the complexities of how that's created. So if we take Flink as an example, an engineer should be able to say, I want you to deploy this jar artifact to a cluster that has 3 task managers running on it and this set of Flink configurations. Not necessarily, as opposed to them having to say, I need a job manager, I need 3 task managers, I need to wait for them to sort of come up and be ready, and then I'm going to submit that jar through a REST API, and all of the sort of complexities that would require to do that. They should just be able to say what they want, and then we can create backend systems that handle all of the complexities of bringing that desired state into existence. And I'll talk a bit about how we do that in just a moment. And then finally, we wanted to be able to simplify how these resources are composed into streaming architectures. And specifically, we wanted to be able to provide this with infrastructure as code. So engineers at Zillow were already very familiar with using Terraform to provision AWS resources. And so we wanted whatever they ended up creating within our system to be just the same way that they're already doing that today into AWS. And actually, we wanted them to be able to mix and match that. So whether you're creating an AWS S3 bucket or a streaming platform Flink job, it all should be done in a very similar way. So what emerged for us was this model of operation that you can see here. So at the very bottom, you can see that there's a consolidated API, like I mentioned, that handles all of the provisioning behavior. So whether you're creating a Kafka topic, a Flink job, or a Kafka access control list, it's all done through one API. And then we have this sort of abstract notion of clusters within our system. And so on the right, you can see our production cluster. On the left, our pre-production cluster. And this is really just a difference of what level of guarantees we have on these in terms of availability and reliability and all of that. In reality, there's actually several clusters within the production cluster, and that's just a matter of so that we can sort of limit blast radius and have separate places for where Flink and Kafka are provisioned. But from the engineer's perspective, they don't have to worry about that complexity. It just all lands on the correct systems for them. And then at the very top layer, you can see this abstraction of a service. So all of our resources that get onboarded get put into this bucket of a service. And then within that service, there's, of course, the notion of environments. And so the engineer that's going to be provisioning resources decides what cluster they want to be on in terms of service level guarantees. And then they assign each of their environments to those clusters. And then when they go and provision things, all of the physical resources that end up getting provisioned end up on the correct cluster for them automatically. And so this is a really nice way for them to just think about how they're going to organize their resources, where they want them to be deployed. It's all done through one consolidated API and experience. So as we kind of set out to build this experience, we realized that this is exactly what Kubernetes is today. It has a declarative API. It has the ability for you to extend its API with custom resource definitions. So we can represent Flink jobs and Kafka topics in the same way that you can with more traditional Kubernetes resources like deployments and pods, if you're familiar with Kubernetes. And so like I mentioned, it has a declarative API, and it already has an established pattern for turning that declarative API into actual backend provisioning. And so it does this, if you see here, it's what's called a reconciliation loop, where you declare a desired state as a resource. So in this case, you might declare a Kafka topic, and you would say this Kafka topic should have some number of partitions, and it should have these specific configurations on it. And then the operator pattern, it allows you to declare some what are called controllers behind the scenes, which respond to these events and then inspect the actual state of the world and compare it against that desired state. So if you submit a new topic to the system, it will say, okay, you said there should be a topic with 2 partitions. I'm inspecting the Kafka system and I see that there is not a topic with 2 partitions. So then I'm going to take an action to bring that desired state into reality. And so in this case, it might provision a Kafka topic on the cluster. And you can kind of see that loop happening here. And it's going to continually do this until it can bring that desired state into reality. And so it turns out that Kubernetes is already well suited for this. We can extend it with our own resource types. And so this basically means we don't have to go build our own API. We can just reuse the existing Kubernetes API and then just extend it as needed so that we can build all of the custom functionality we need for our specific engineers. And the other benefit of using Kubernetes in this way is that it has this plug and play compatibility with all this existing tooling. So there's already a Terraform provider for Kubernetes. There's already a bunch of CLI tools and IDEs for interacting with those resources. And there's already a built-in authentication and role-based access control system and a way of isolating resources using namespaces. And so what we decided was that rather than going and building our own system, we can just simply extend the Kubernetes system, build some custom operators behind the scenes, or maybe in the case of Flink, and I'll talk about this, just take one off the shelf but start using it. And then we can really give one common and intuitive way for our customers to set up all of the different resources within our systems, even if the underlying infrastructure isn't necessarily consolidated. Our customers won't, and by customers I mean the engineers using our system, won't have to worry about it. So like I mentioned, as we sort of set about building these backend systems, we realized that Lyft had already open sourced a Flink operator for working with Kubernetes. And so we happily took that off the shelf and started using it and found that it was really good. So I would just want to do a shout out to them. I know they've actually presented at Flink Forward in the past. They've done a really nice job open sourcing this technology. Flink on containers is awesome. It's just a really nice way of running Flink, and it allows us to dynamically provision clusters without having to sort of actually provision physical resources within AWS. It also has some really nice features, like it has automated deployments. So all you do is you change, say, the image that you want deployed, a Docker image in this case, and it will handle taking a save point in your job, starting up this new set of Flink resources, job managers and task managers, and then deploying that new image, or in this case, a new Flink job on that new cluster that it just stood up. And in the case of a failure, it'll actually automatically roll back to that previous cluster and restart the job. So it's got a lot of really nice things that up to this point our Zillow engineers were sort of having to do in a manual way. So whether it was submitting jobs through Flink's UI or building complex CLI tools or continuous integration scripts to do it. So, and really the best part about this was that we didn't have to build it. We took it off the shelf. We were able to actually contribute a couple of small changes to it. So big shout out to the Lyft team for making this awesome operator. So we just pulled this off the shelf and included it into our Kubernetes ecosystem. And then the other thing that we did is we went and built a custom Helm chart to sort of encapsulate that the Flink operator's behavior. So with their operator, what you do is you create a Flink application resource. It's a custom Kubernetes resource. And then Helm allows us to package this all up into our own sort of configuration syntax and then include additional things like we, in addition to deploying a Flink application resource, also deploy a service account in Kubernetes, which allows the Flink job to assume an IAM role in AWS, which allows it to basically assume an identity within AWS so that it can access other AWS resources, secrets, S3 buckets, things like that. And it allows us also to include things that are specific to Zillow. So we have, just for example, we mark up the Flink job with metadata around what team owns it and what the service it is. We have this concept of compute class, which allows them to sort of determine what level of CPU to memory they need for their job so they can fine-tune their resource utilization. They have the ability to sort of fine-tune how their parallelism gets set up within their job. They can submit any sort of Flink configuration that they want to be present on their job, and then this configuration block here is what's specific to the Flink operator that we're adopting, and so they can configure that however they want to as well, including what Docker image ends up getting used to run their Flink cluster. So then I mentioned that we pulled a Flink operator off the shelf, and then now we were sort of trying to figure out, okay, how do we bring Kafka now into this new provisioning experience? And so what we realized that there wasn't really a good pre-existing solution here. And so what we needed to do is we needed to build some operators that could build a bridge between the Kubernetes API and the reconciliation loop that I talked about, and then interacting with the various Kafka APIs. So when a Kafka topic resource is created, we needed some topic operator to be invoked, which would then do all of the necessary interactions with the Kafka API to make that Kafka topic, to bring that Kafka topic into being. And so we ended up using a technology called the Kubernetes Meta Controller, which is essentially just a backend service that allows you to sort of register arbitrary custom resource types with it. So in this case, we registered a topic resource and an ACL resource for managing permissions to those topics. And the Meta Controller allows you to then deploy just simple HTTP services that implement a sync method. So anytime one of these topics is created by the Kubernetes API, Meta Controller becomes aware of it. It figures out which operator you registered for that resource type, and it simply calls a sync method on that over HTTP. So this was just sort of the easiest way for us to get started with operator development. There are more complex ways you can go about it, where there's like a whole set of SDKs for building operators, custom operators using the Go language. But we really wanted to be able to develop it in any language we wanted. In this case, we used Kotlin, so we could plug into all the JVM SDKs for interacting with Kafka. And so this was just a really quick and easy way for us to get tied into that reconciliation loop and to build an operator without having to invest too heavily in learning, say, a new language, which would be the Go language, and without having to get too much into the details of how the Kubernetes APIs worked. But also knowing that we could always sort of take a deeper step into the pool later and build a more complex operator if we wanted to, without fundamentally changing anything about how the engineering teams interacted with our API. So it was kind of a win-win for us in that case. And so now that we've got all of these different resource types within our provisioning API and we're using Kubernetes, we wanted to be able to use then Terraform to be able to interact with those resources so that our engineers could build complex streaming architectures as simple Terraform configurations. And then Terraform can do a lot of the heavy lifting of figuring out how to sort of interact with the Kubernetes APIs, how to compose these resources into a dependency graph so that they can be provisioned in the correct order. And so here you can see we went and there was already a Terraform provider for Kubernetes, and we were able to simply extend that Terraform provider with our own resource types. And so here you can see we have a service resource type. And so this resource type is responsible for provisioning a namespace in Kubernetes that allows us to isolate these resources within so everything within namespace is sort of isolated from any other namespace. And so we can give our engineering teams just permissions to the namespaces that are specifically for their service. In this case, the service that they've registered and onboarded with us. And then everything that gets created in here, whether it's a Flink job or a Kafka topic or a Kafka ACL, it all goes into this namespace, and they have the ability to access it in a very scoped way. And so then we added another resource type for Kafka topics. It has its own schema for configuring how many partitions, what the schema of that will be. So I mentioned the schema registry. So this is sort of a tie into that schema registry, so you know exactly what data to expect on that Kafka topic. Notions of privacy, and there's a lot of other things that can be configured here, but this is just a simple example. And then most importantly, you can see that this is specifically tied to a service. And so this is what I talked about of using Terraform to compose resources. So Terraform will know that because this resource depends on this resource, it needs to either provision or make sure this resource is provisioned first before it can then provision this resource. And then similarly, to create this ACL, which gives specific permissions to that topic, it's going to wait for that topic to be created before then going and creating this. And so it allows you to create these really nice dependency graphs of resources and then deploy them all in one sort of declarative step. And this becomes really powerful when you start to think about other types of Terraform providers that already exist. And so if we go back to that example before of a Flink job, reading and writing from Kafka, maybe also writing to an S3 bucket, you can compose that all as one single Terraform project or Terraform module, where you're mixing and matching all these different resource types. Maybe you want to also include a monitoring aspect, to use the Datadog provider to create a monitor for your Flink job. So everything here on the right-hand side can then be provisioned as one single Terraform configuration, so that when we go ahead and deploy this Flink job using Helm, then we'll be able to, it'll just have everything it needs to already deployed and ready to go. The other thing that we added in to this is that anytime a new project or service is onboarded, and I'll talk a bunch about this during the demo, is we wanted to have a standardized way of doing continuous integration and continuous deployment for whether you're deploying a Flink job using Helm or whether you're deploying your infrastructure resources like topics using Terraform. And so anytime a project is bootstrapped and onboarded within our system, we automatically generate all of the CI/CD scripts for executing. So in the case of Flink, we build it, we test it, we publish a Docker image, maybe we publish some schemas, and then we deploy it to the various environments that they have configured. In the case of Terraform, we have plan and apply steps, which allow them to sort of evaluate the plan. If you haven't used Terraform, the plan is basically just saying, here's what I'm intending to create based on what's already there and what's not. It's also declarative, just like Kubernetes. And then the apply step is what takes that plan and actually does all of the API interactions with the Kubernetes API or in the AWS API, if you're using that provider, to actually turn all of those resource specifications into actual resources running on your infrastructure. The other thing that we do for every project is we've developed a standardized monitoring approach. So anytime a new Flink job is created, for example, we generate a new Datadog dashboard. So we use Datadog within Zillow, and it comes pre-populated with all of the things that we have found to be useful when monitoring Flink application. So whether or not the job is running, whether checkpoints are happening on a regular cadence, whether the checkpoint size is steady or sort of ballooning out of control, whether the job is restarting, et cetera, et cetera. And then we also have Kubernetes resource monitoring here as well. So all of the containers that end up getting spun up for a given Flink job, we monitor the health of those and tell them like how much CPU they're using, whether they're being throttled or not. And so it's just a really nice, we found just from talking with our engineering teams that this is probably the single most valuable thing that we've even given them to this point, because it takes so much load off of their team to have to figure out all of these complexities of monitoring a Flink job. The other thing that I think I'll just mention that we really prioritize and I think turned out really well for us is that we really took open source projects as an inspiration for how we built out all of our different things that sort of comprise the streaming platform. And so we spent a lot of time building really high quality documentation, and we use a tool called Docsify, which allows you to just write your documentation as Markdown, and then it automatically turns it into a really nice looking HTML experience, including search and things like that. We also spent some time working on branding. I know you might think, internal platform, like why are you spending time on branding? You don't have a marketing department to work on this stuff. But I think just spending a little bit of time on these types of things and giving sort of an identity to what you're building, it really helps inspire confidence in the technologies, and it allows engineering teams to kind of see what you're doing and take it very seriously. And for us, it really cut down a lot on sort of confusion and like, should I use this or shouldn't I use this? And we've gotten really, really good feedback from our engineering teams on this, and they really appreciate it. So something I would just recommend, you don't have to spend weeks on this kind of stuff. It's just going a little bit of extra effort to just really have that little bit of extra impact on the engineering teams being able to sort of onboard and use what you're building. And then the other thing I didn't mention is that we have taken a very standardized approach to how we do versioning within our system, and we have release notes that get attached to our versions as well. And so for all of our kind of major platform components, like we publish a Docker image that's sort of specially set up to run Flink, plus some of our like custom things like how we do logging and how we do configuration. And so this has been a really good way for not only for us to sort of make sure we have sort of continuity between versions and that things continue to work, but it's really super helpful for our customers to understand, and by customers again I mean our engineering teams, like what's in this new version, is it safe for me to take this? It's significantly cut down on the amount of questions we get as again engineers are in this self-service decentralized model where they're managing all of their own resources in their own projects. This becomes incredibly important for allowing them to do that. And then the last thing I'll mention before we jump into the demo is that we have made quite a few investments into a CLI tool that we give out to our engineering teams. So that invariably there's a lot of things that can be automated about how to interact with resources, how to provision resources, how to get projects bootstrapped so you can start creating Terraform configurations or developing a Flink job. And so this tool, one of the more important things that it does is it automatically handles all of the Kubernetes authentication and role-based access controls. So using each engineer's, we use Okta for authentication. It figures out who they are. It figures out what roles that they have for the various services that have been onboarded for their team. And it automatically sets up all of the API calls so that when you interact with Kubernetes, it just automatically picks the right context and the right authentication context, so you're interacting with just the resources that you have access to. It also has methods for bootstrapping new Terraform and Flink projects, and so I'm going to go through all of this in the demo because it's a huge part of our experience. But basically, you can, with one simple command, you can get a fully functioning Flink project that's already configured for getting deployed to our shared infrastructure, already has all the Helm configurations set up, as well as a lot of best practices around like configuration and logging and things like that. And then the last thing that I'll talk about is that we also added in some nice helper functions or commands for interacting with Flink jobs once they're already deployed. So, for instance, accessing the UI, you type in a simple command and it will do all the port forwarding into Kubernetes so that you can access the Flink UI, as well as getting access to logs and monitoring dashboards without having to get really deep into Kubernetes interaction. And this is something we're continuing to add functionality to as well over time as we sort of identify areas that would benefit from automation. And as we talk with our engineering teams, this is an area where we see continued investment being valuable. So with that, I'll jump right in and talk, kind of show you exactly what it's like to be an engineer at Zillow and all of the various aspects of provisioning stream processing resources into an end-to-end example. So the first thing I'm going to show you is how our teams can use the CLI tool that I just talked about to initialize a new Flink project. So before doing this, they would have worked with us to onboard their service. So they would register their service name in the various environments that they have. And then we would automatically provision Kubernetes namespaces and roles and permissions for them so that they have access to provisioning Flink and Kafka resources in those namespaces. But once they've done that, they can run this update creds command, which is going to look up all of the roles that they have within the streaming platform, and it's going to set up a Kubernetes config file so that they can then start authenticating with our Kubernetes cluster and create those resources. The next thing, if they want to initialize a Flink project, is they need to set up a configuration file. So I've added one to this directory already, and this just tells the streaming platform CLI tool what service it's dealing with, what environments are meant to be configured, and whether or not Flink is enabled. So in this case, it will be. So now I can run another command, flink init, and this is going to look at this configuration file and it's going to set up a fully configured Flink project for me that's going to be set up and ready to deploy to our remote infrastructure. So I give it a Java package, and there we go. And if I take a look in the structure, you can see there's a whole bunch of files here. So let's open this up in IntelliJ so that we can dig in. So here you can see the Flink project that I just initialized loaded up in IntelliJ. And the first thing I'll call out is that there are some Helm configurations. So this is how the Flink application gets deployed to Kubernetes. And most importantly, there's different Helm configurations per environment automatically configured. So this is where I can, for example, configure per environment parallelism. I can set up my Flink configs and everything I might want to customize about this Flink job. There's also a set of example projects in here as well, or example Flink applications, one that reads and writes data with Kafka, and then another which generates a random set of numbers. So this is for engineering teams that may not be familiar with Flink. This is a really nice way to get them started, and these are all fully configured to utilize the per environment configuration settings here as well as ones that get set up in this resources folder. There's also a GitLab CI specification. So this is for our continuous integration and deployment. We use GitLab. And so this automatically sets up build and publishing steps for Docker images, and then it has deploy steps for each of those environments, and then automatically invoking the various Helm and environment configurations that have been set up for that as well. Next, you'll see that there's a Docker file in here as well. So this uses a custom Docker image that we publish for our engineering teams, which extends the default Flink Docker images and just adds some standardized logging behavior, among other things. And then there's two Docker Compose specifications here. One that sets up a Kafka cluster local on their machine. So this is a really nice way for them to test Kafka connectors locally. And then there's another one, which in addition to sending up a Kafka cluster, it also stands up a Flink cluster and then submits the job from this local project to it. So engineers can simply run a script and it'll build this entire project using Gradle. Generate that shadow jar, and then it's going to build a Docker image and embed that jar file inside of it. And then now you can see that it's standing up a Kafka cluster and a Flink cluster. And so this is going to set up a fully functioning end-to-end containerized environment for my Flink job. And it's going to let me verify that everything works in a containerized environment. So the code that's talking to Kafka and all of the various dependencies that I've embedded in my shadow jar, and that gives confidence to the engineers that when they do go ahead and deploy this to a remote environment, it's just going to work. So now I can run this, access the UI for this local Flink cluster, see that my job is running, and do anything else that you might expect for a Flink cluster. So then once the engineer is done doing their development work, and they've verified that everything runs locally, then they're going to want to provision those Kafka topics in our actual remote environment so that they can then deploy this Flink job and it will be there for them to interact with. So we have another command, streams Terraform init. So this is going to read that same specification file, and it's going to find my various environments, and it's going to set up a Terraform project here inside this project as well, with per environment configurations as well, just like you saw with Flink. And then I can come into this topics directory, and I can provision a couple of topics in here. So then if I go to the dev environment, I can run Terraform init to get this project ready. And then I can run Terraform apply. And this is going to see that there's 2 new topics that need to be created. Tell me what they are. And you can see that 2 are getting created, and I can say yes. And so now this is interacting with the Kubernetes API, and it's provisioning those Kafka topics using all of the different systems that I talked about previously. So now this is ready to go. So I could push these Git changes to GitLab, and then a CI pipeline would automatically kick off to then deploy this to Kubernetes. So to save some time, I've already got one standing by, so I'll go ahead and kick that off. So the build and Docker image steps are done, and now we're going to be ready to deploy to dev. There we go. So this is going to take just a moment. So while this is loading, I'm going to show you another cool feature we have. So I mentioned commands for accessing Flink resources that have already been deployed. So we can run this dashboard command. Actually, I need to step up a directory. Streams Flink dash mdev. And this is going to print out the URL to a dashboard for monitoring that Flink job, which I mentioned from before. So we can load that up so we can watch this Flink job get deployed. And so here you can see what this is doing is it's starting to stand up some Kubernetes containers for running Task Manager and the Job Manager, and then it's going to wait for that to become ready. And then once the Flink cluster is up and ready, it's going to then submit my job to it automatically. So we'll be able to see that happening here in just a moment. Then the other command that's pretty cool is we can, if we need to access the Flink UI for some reason, we can do it in the same way as we just printed out that dashboard. And this is going to go and look up the Flink service running on my Kubernetes cluster, and it's going to set up port forwarding automatically so that I can then access my Flink UI running on the cluster from my local computer. So here you can see that my Flink job has now been scheduled on this cluster, and it is running. And here we can see that the monitoring dashboard is starting to pick it up. And so I've gone from a empty directory to a fully configured Flink project. I've provisioned some Kafka resources that it's going to end up using, and now I have a full monitoring experience already set up for it, and I'm ready to go. So this whole end-to-end provisioning experience has drastically simplified the process for our engineers to bring these stream processing workloads into production and run them. So anyway, that's it for my demo, and that's it for my talk. So I just wanted to thank everybody who took the time to come watch this. I hope you learned something new. And I also wanted to take some time to thank all of the organizers for this conference. It's an amazing event, and I'm really excited to be a part of it. So with that, I'll open it up to questions, and we can take it from there. Thanks.